You ever look at a fossil or maybe just an old rock and wonder, how in the world can anyone say that's millions or even billions of years old? I mean, it seems like some kind of magic trick, right? But it's not. It's all based on one of the most reliable clocks in the entire universe, the atom itself. So how do we actually read this atomic clock? Let's dive in.
Right, let's get specific. You hear this all the time. A T-Rex bone, they say, is 70 million years old. But how? How do we get a number that specific from so long ago? It's definitely not a guess. To get the answer, we got to understand how scientists can read a clock that's been ticking away silently inside rocks for eons.
Okay, so before we even get to the clock, we have to wrap our heads around the incredible scale of what we're measuring. We're talking about deep time, eras that stretch for hundreds of millions of years. Look at this chart. Our entire human history is just this tiny, tiny little sliver right at the very top. So to measure something this vast, you need a tool that is unbelievably consistent and ancient.
To really get this huge concept, let's scale it way, way down with a simple analogy. Just for a minute, forget about atoms and billions of years. Let's just talk about a fish pond. So, imagine you build a little pond in your backyard. You set it all up, you know exactly how it starts, and you create one simple rule that controls everything. The most important part here is that it's a closed system. Nothing gets in or out unless you know about it. This little pond is going to be our model for telling time.
So here's the puzzle. You start with something you know for sure. 30 fish. You've got a constant, predictable rate of change. One fish vanishes every 8 months. And it's a closed system, remember. No new fish are hopping in. So, here's the cool part. If you come back way later and find that pond is empty, you've got all the clues you need. You can actually work backward and figure out exactly how much time has passed.
And the answer is 20 years, right? 30 fish times 8 months for each fish, that gets you 240 months, which is exactly 20 years. It's pretty simple when you break it down. You knew the starting amount, you knew the ending amount, and you knew the rate of change. That's it. That is the fundamental logic behind radiometric dating.
Okay, now let's see how this very simple idea scales up from our little backyard pond to the real world of geology. We're going to swap our imaginary fish for something way, way smaller and incredibly predictable. We're talking about atoms.
So, inside a lot of rocks, you've got these unstable or radioactive atoms. These are our fish. Over time, they just spontaneously disappear. Or, to be a bit more scientific about it, they decay. They transform into a new, stable kind of atom. And here's the most important part. This whole process happens at an unbelievably predictable rate.
Instead of saying one fish every 8 months, scientists use this concept called half-life. It's just the amount of time it takes for exactly half of the unstable parent atoms in a sample to decay into stable daughter atoms. And every single radioactive element has its own unique, unchangeable, constant half-life.
This graph really shows you how it all works. Let's take potassium-40, which decays into argon-40. It's got a half-life of 1.3 billion years. So you can see here, if we start with 100% potassium, after that first 1.3 billion years, boom, we're down to half. After another 1.3 billion years, so that's 2.6 billion total, we're down to a quarter. It just keeps halving over and over with perfect timing. It's an incredibly reliable countdown clock.
Okay, so this atomic clock is amazing. But how does it actually get started? How do we set it and how do we read it? Well, the answer often comes from one of nature's most dramatic shows, a volcanic eruption.
Way deep inside the Earth, in these huge chambers of molten magma, crystals start to form. And as they grow, they trap elements from their surroundings, including unstable parent atoms like our potassium-40. But here's the trick. The daughter atoms, in this case argon, are a gas. They don't fit into that tight crystal structure, so they just get pushed out as the crystal grows.
And then the volcano erupts. All that magma gets blasted to the surface. As it cools down and hardens into volcanic rock, those crystals with all the potassium get locked into place. Any argon gas that might have been floating around gets burned off by the incredible heat. This exact moment of cooling, that's time zero. The clock starts with 100% parent atoms and 0% daughter atoms trapped inside.
So now the clock is ticking. Millions of years go by, and that trapped potassium is slowly, steadily decaying into argon. But now, because the rock is solid, that argon gas is trapped right there inside the crystal.
So when a geologist comes along, they can literally crush the rock and measure the ratio of the parent potassium to the daughter argon. And if you know that ratio and you know the half-life, you can calculate exactly how long it's been since that rock cooled down. It is the fish pond puzzle, just on a cosmic scale.
Now, this isn't just some clever trick you do in a lab. This technique completely changed everything we thought we knew about our planet and our history on it. This is how we unlocked the story of deep time.
So, what did this discovery really do for us? Well, for the first time ever, it gave us absolute dates. No more just guessing. This is the tool that let us build that whole geologic timescale we saw earlier. It gives us the actual timeline for evolution, showing us precisely when animals like the dinosaurs lived and when they died out. It lets us piece together the history of our planet's continents and oceans. And, maybe the biggest one of all, it was the final proof that our planet is billions of years old, giving science the enormous timescale that huge processes like evolution actually need to work.
You know, the discovery that we could read time in the very fabric of rocks was a massive leap for science. It really makes you wonder, if there are clocks ticking away in stones all around us, what other hidden languages and secret histories are embedded in the universe, just waiting for us to figure out how to listen?